जी सही है।
Good evening, sir.
Yes, good evening. Yes, today thermodynamics. Yes, how many topic?
Yes, sir. Yes, sir.
Today thermodynamics. Yes.
हाँ जी, sir.
Today topic thermodynamics.
हाँ जी, sir. Yes, sir.
Yes, let me start.
Am I audible, sir?
Yes, yes, you are audible. Fine.
Okay. ठीक. Sir, board visible है ना properly?
Yes, yes, clear. All is fine. Yes. First is basic thermodynamics. What the main application of thermodynamics and what is thermodynamics?
Can I start, sir?
Yes. Sure.
So today we will discuss about thermodynamics. As the word itself explains, it is the combination of two words, thermo and dynamics. Thermo literally means heat and dynamics means motion. So, thermodynamics is that branch of science which deals with quantitative relationship between heat and various energy changes. And when we confine our study to the chemical system or chemical substances or chemical reaction, that branch of science is known, that restricted branch of thermodynamics is known as chemical thermodynamics. In thermodynamics, we will read about some basic terms. First is system. So what is system? The problem which we are dealing with is simply a system. For example, if we are carrying out a reaction in a beaker, so in that case, that beaker will be our system, and apart from that system beaker, everything around us is surrounding. System and surrounding together makes universe, and system and surrounding are separated by a boundary. That boundary may be static or moving. For example, when I take the example of reaction taking place in a beaker, then the walls of the beaker are our boundary. And when we consider pressure volume work, in that case, the surface area of the piston which is moving up and down is example of the boundary which is moving. And in first case, the reaction in beaker, the boundary is our static. Now coming to the type of system. We have basically three main types of system: open system, closed system, and the isolated one. Now coming to our first open system. In open system, the exchange of both matter and the energy takes place. For example, when we take the water in an open vessel, this is the example of our open system, because when we provide heat to this vessel, then water heated up and it may convert into vapors. So in this case, our content, that is water molecules, are converted into the vapor molecules. So our mass is exchanged. Also, exchange of energy is also takes place, because in this, heat energy is consumed to carry out the vaporization of water. Now coming to the next case, closed system. This system in which only exchange of energy possible, but we can't exchange mass. Here in this system, मास का एक्सचेंज नहीं हो सकता. फॉर एग्जाम्पल, अगर हमने बोतल में एक कंडक्टिंग वेसल ले लिया, उसमें है अपना वाटर, और उसको हम हीट, और वो वेसल है जो अपना क्लोज है, और हमने हीट प्रोवाइड की है सिस्टम को, देन जो वाटर मॉलिक्यूल्स हैं वो कन्वर्ट कर सकते हैं अपनी वेपर फेज में, बट वो एस्केप आउट नहीं होंगे सिस्टम से. So that means here only exchange of energy takes place. Energy is provided to convert water molecule in liquid phase to vapor phase, but here no change in the mass of water molecule takes place within the whole system. Now coming to the another last one, isolated system. In isolated system, here neither exchange of energy nor mass. आइसोलेटेड सिस्टम में ना ही अपना एनर्जी का एक्सचेंज होगा, ना ही मास का एक्सचेंज होगा. फॉर एग्जाम्पल, अपने पास जो थर्मोस्टेटिक फ्लास्क होते हैं, बोतल होते हैं, जिनकी आइसोलेटेड वॉल्स होती हैं, जिनमें हीट एक्सचेंज नहीं हो सकता. सो दैट इज अवर आइसोलेटेड सिस्टम. In this, no exchange of mass and energy takes place. Here, there are two separate things: isolated system and adiabatic process. In adiabatic process, there cannot be exchange of heat only, but there can be exchange of work. But in our isolated system, exchange of heat, work, either form of energy is not possible. Adiabatic में अपना बस हम हीट का एक्सचेंज नहीं कर सकते, वहां वर्क डन पॉसिबल है, बट इसमें neither work is done on the system nor work is done by the system. That is the main basic difference between isolated process and adiabatic process. Now coming to the another term, state of the system. And now coming to state of the system. State of the system is defined by some specific thermodynamic variables like temperature, pressure, volume. We say thermodynamic process occur when the value of these thermodynamic parameters change. We say when a thermodynamic process occurs, then initial and final state of the system changes. For example, when I consider pressure, volume and temperature, in initial state, I have the value of these parameters P1, V1 and T1. And in final state, I have the value of these parameters, which changes to P2, V2 and T2 respectively. Then state of this system, initial state of system is defined by these parameters. final state is defined by this parameter, and change in the state of system is defined by the difference between these variables at different states. Now coming to the thermodynamic processes, as already explained, thermodynamic process is said to occur when change in these properties variables occurs. Thermodynamic process may be of four types. First one is our isothermal process. Second one is isobaric process. Another is isochoric, and last one is adiabatic process. Now coming to isothermal process.
Yes.
Sorry, isothermal process. As the name suggests, iso and thermal. It is the combination of two words, iso and thermal. Iso means same, thermal means temperature. When the process is carried out at constant temperature, then this thermodynamic process is known as isothermal process. Now coming to isobaric process. When the process under thermodynamic considerations is carried out at constant pressure. Baric stands for pressure, since it is the unit of pressure, and iso again same meaning. So we can say when the process is carried out at constant pressure, it is known as isobaric process. Now coming to isochoric process. In isochoric process, there is volume constancies during the reaction. Now coming to the last one, adiabatic process. Adiabatic process, the process in which there is no heat change during the reaction. Now coming to the another terms which thermodynamics deals. Basically, thermodynamics deals with macroscopic system. What is this macroscopic system? This system which deals with a large number of atoms or molecules. Now, after this, what is our macroscopic property? The property associated with the collective behavior of all these particles is known as our macroscopic property. Actually, this is also one of the advantage or disadvantage in this branch. In thermodynamics, we deals with the collective behavior of the system, but not with the individual particles. Here we deals with collective behavior, that is macroscopic property. It may be extensive. It is of two types. The property may be extensive or it may be intensive. Now, what is extensive property? The property which is amount dependent, which depend upon the only on the amount of the substance. For example, mass, volume, heat capacity are our extensive property. For example, अगर हमने एक बॉक्स है उसमें हमने 2 किलोग्राम चीनी शुगर ले रखा है और उसमें हमने दोबारा 1 किलोग्राम शुगर ऐड कर दिया, तो टोटल अमाउंट ऑफ शुगर इज 3 kg. That will not change. That is basically the sum of first one and the last one which we are adding. So it is the extensive property is the overall sum of the amount present in the system. But second one is our intensive property. It depends upon the property or nature of the substance. Nature of substance present in the system, not on the amount. For example, अगर हमारे पास एक सिस्टम है, उसको हमने सिस्टम है जिसमें हमारे पास है 4 लीटर वाटर लगा लो, 4 लीटर वाटर है हमारे पास। अगर हमने उस सिस्टम को एक बाउंड्री से डिवाइड कर दिया, तो पहले सिस्टम का टेम्परेचर था T1, डिवाइड करने के बाद भी अपना सिस्टम का टेम्परेचर बोथ पार्ट्स में अगर हमने कोई भी एक्स्ट्रा वर्क, मैकेनिकल वर्क या एनर्जी प्रोवाइड नहीं की है सिस्टम को, तो दोनों पार्ट्स में टेम्परेचर सेम रहेगा और सेम इन द केस ऑफ प्रेशर. सो टेम्परेचर, प्रेशर are our intensive properties. So these don't depend upon the initial and final amount of the substance. These depend upon the nature of the substance. Now, also here we may define specific heat. Specific heat is an intensive property, whereas the heat capacity is extensive. So any extensive property can be converted into intensive property, as in case of heat capacity, by dividing it by its molar mass or by converting it into the unit amount. Now, coming to the various law on which thermodynamics based. There are certain laws on which our thermodynamics is based. These are 0th law, 1st law, 2nd law, and 3rd law. Now coming to the basic one, 0th law. 0th law states that when two systems A and B are in thermal equilibrium with the third system C at a constant temperature, then these two systems are also in equilibrium with each other. So, 0th law basically introduces the concept of temperature. Now coming to first law of thermodynamics. First law of thermodynamics states that our energy of a system is conserved, but it can be changed into one form to another system. Mathematically, first law is given by this reaction. That is, it states that change in internal energy is equal to sum of heat changes and work done during the process. And more precisely, in thermodynamics, this work done is pressure volume work, PV work, and this reaction changes to during the case of expansion. Work done during the case of expansion is negative, because in this case work is done by system, and in case of contraction work done is positive. Similarly, in the case of heat change in the process is taken as positive when heat is given to the system, and in another case when heat is given by the system, then this DQ is taken as negative. Now coming to the units. Internal energy is measured in units of joules. Similarly, in the case of heat and work done. Now coming to second law of thermodynamics. Here we have seen the first law of thermodynamics introduces the concept of internal energy. Now coming to the another one, which is second law of thermodynamics, it deals with the spontaneity of the process. It tells us whether the process will be spontaneous or not. For example, the heat can flow itself from a hot body to cold body, but itself it cannot flow from cold to hot body. This is not explained by the first law of thermodynamics. Now second law of thermodynamics state that only with the help of external agencies heat can flow from cold body to hot body. It also states that the 100% conversion of heat into work is not possible, which is also seen in the case of Carnot engine, because we are dealing with the real system, not the ideal one. Carnot engine is the most common application of second law of thermodynamics. In Carnot engine, heat is taken from the source to do some mechanical work, and the rest of the heat, unused heat, is given to the sink, which is at lower temperature. In Carnot engine, basically, let us consider this is our system. Heat is given to the system. Let us take Q1 amount of heat is given to the system at temperature T1, and some work is done by the system, and rest of the heat, extra heat, is evolved by the system to the sink, which is at lower temperature T2, and let's consider Q2 amount of heat is evolved by this system. In this, efficiency of Carnot engine is given by eta, which is the ratio of output to the input. Here output is our work done by the system. Since it is work done by system, it is negative. And input is our heat given to the system. Heat given to the system. That is Q1. Now, upon mathematical calculations, we find that efficiency of Carnot engine is given by T2 minus T1. Here we simply see that the efficiency of Carnot engine is dependent only upon the initial and final temperature difference, not upon the nature of material which we are taking under consideration. So this is our final expression for efficiency of Carnot engine. Here we can discuss about the concepts ideal case or irreversible engines. Ideal case is that one in which our system is 100% efficient. The case when eta is 1. When will our system is efficiency will be equal to 1? Ideally, it is not possible. In our day-to-day life, we deal with real systems in which value of our coefficient is less than 1. Now, coming to the concept entropy. Here in the second law, we we have not taken into account the entropy, that is randomness. What is the randomness of molecules, how the molecules are arranged. Second law of thermodynamics basically deals with the feasibility of the process. Now coming to third law of thermodynamics. Thermodynamics, third law of thermodynamics introduces the concept of residual entropy. What is residual entropy? The entropy contained within the system at lower temperature. Since third law basically states that a perfectly crystalline substance at 0 Kelvin temperature possesses zero residual entropy. Means entropy of this system at 0 Kelvin will be 0 as stated by third law of thermodynamics. But in actual processes, day-to-day process, it is not possible. For example, in case of carbon monoxide, nitrogen oxide, the residual entropy is not 0. What does it mean? It means that the molecules are not properly arranged even at 0 Kelvin. Means they have some orientation movement. That residual entropy is given by the formula F, which state our entropy is equal to K ln W. Here K is our Boltzmann constant. More specifically, it should be Kb. Now, and W is our number of orientations. For example, in case of carbon monoxides, we have the value of W2. Means we have two orientations, whether it is connected by carbon or it is connected by oxygen, CO. Now, this is all about third law of thermodynamics. सर मेरा बेसिक्स में एप्लीकेशन से इंट्रोड्यूस किया तो मैंने एप्लीकेशन वाला पार्ट रह गया, वो मैं करते करते याद भी आ गया था, बट उसको कंटिन्यू किया कि थर्मोडायनेमिक्स हम कि किस चीज के बारे में बताता है, एक्सटेंट ऑफ रिएक्शन, रिएक्शन की फिजिबिलिटी, स्पॉन्टेनिटी, वो वाला रह गया। और मेन की इसके डे टू डे लाइफ में यूजेस क्या है, जैसे कार्नोट इंजन, रेफ्रिजरेटर और जैसे एग्जॉस्ट फैन सर, वो मैं सर याद आ गया था, बट मैंने इसको कंटिन्यू रखा। वो शुरू में ही जब डेफिनेशन बोली थी उसके बाद ही इंट्रोड्यूस करना था सर वो कंसेप्ट, सिस्टम सराउंडिंग से पहले वो स्किप हो गया सर।
कोई नहीं, वो बाद में आप बता दीजिए, वो तो फिर वो जब आप स्टार्ट करेंगे वंस अगेन उसमें हम देख लेंगे। इसके बाकी और जैसे जूल्स ऑप्शन इफेक्ट है, जूल्स ऑप्शन कॉफिशिएंट है, वो चीज हम देखते हैं इसमें, वो भी स्टडी किए हैं आपने?
हाँ जी सर।
यस, कैरी ऑन, इसको कीजिए आप।
ओके सर। कमिंग टू जूल्स लॉ, Joule's law states that for the ideal gas, change in internal energy with change of internal energy with volume at constant temperature is zero. This is our Joule's law. Now coming to Joule-Thomson effect. Joule's law is basically for ideal gas. it deals with change in internal energy divided by change in volume. It simply states that change in internal energy is zero, which means there is no force of attraction between the gaseous molecules, which can only occur in the case of ideal gases. But in the case of our real gases, we listen about the expansion or contraction, which is always possible with change in internal energy if there are force of attraction or repulsion which the gas can feel. Now coming to Joule-Thomson coefficient, Joule-Thomson effect. Joule-Thomson effect states that when a gas expands adiabatically, the first condition is expansion of gas. First condition is expansion, means work done negative. When a gas expands adiabatically, from it, second condition is expansion. Which type expansion? Adiabatic or isothermal? Adiabatic expansion. When a gas expands adiabatically from a region of high pressure to the low pressure, it is accompanied by cooling. Mathematically, it is given by mathematically we can say here one point is skipped. Our reaction is carried out at isoenthalpic conditions, means enthalpy of our system remains constant throughout the process. Here the whole process, this effect is called Joule-Thomson effect, and the mu associated with this process, which is the ratio of change in temperature to change in pressure at constant enthalpy conditions, is known as Joule-Thomson coefficient. Now coming to mu, Joule-Thomson coefficient. Now coming to this Joule-Thomson coefficient, for the ideal systems, mu is 0. That is, since we are considering the expansion, so P2, our final pressure will be less than the initial pressure, so curly P will be negative. Also, mu 0, it states that change in temperature 0. What does it mean? It means that in case of ideal gas, there is no forces, no any forces of attraction or repulsion. Means this can be also be proved by taking mathematically the other equivalent expression, which is this. This can be simply mathematically derived. Now coming to the case of real gases. The first case, when change in temperature is this delta T is positive. when this change in temperature is positive, that is T2 greater than T1. In that case, our mu will be negative. This can be this mu is negative, and also we can say that there will be heating of the gas, which can be derived since we know that sorry, this have been skipped. Since we know that this comes from our second sorry sir, वो term याद नहीं आ रही, second equation of state. Now when this is mu, when mu is negative, that is सॉरी सर, ये मैस हो गया सारा, तो इसको मैं दोबारा देख लूंगी, बाकी अभी ध्यान तो आ गया मेरे कि ये कैसे था एक्सप्रेशन, इसमें इसका मैथमेटिकल डेरिवेशन वो मिक्सअप हो गया। yes. जो हम हीट कैपेसिटी का और वो देते हैं, वो इसको मैं दोबारा देखती हूँ सर, क्योंकि मैं एक्सप्रेशन तो ड्राइव नहीं कर पाऊंगी, बट उसको जो टर्म्स हैं जैसे बोलना है वो वाली चीजें स्किप होगी सर। इसको मैं देखती हूँ सर कि मैं इसमें सर कुल
जूल थॉमसन कोफिशिएंट में इन्वर्जन टेम्परेचर भी होता है, क्या होता है इन्वर्जन टेम्परेचर?
हाँ जी सर, इन्वर्जन टेम्परेचर the temperature at which real gas behave like as ideal gas. Is it sir?
फॉर्मूला क्या है इन्वर्जन टेम्परेचर कैसे निकालते हैं? Ti इक्वल टू
सर हाँ जी सर, उसमें सर ये बेसिकली इधर से ही आ जाता है, एक Ti is equal to 2A by RB. In case of inversion temperature is the condition when we deal with the ideal case. In that case, mu will be 0. So from that point, our B minus 2A by RT will be 0 because Cp is constant. So Ti inversion temperature can be derived as Ti is equal to 2A by RB.
Yes. Joule Thomson coefficient is ideal value, ideal gas mu Jt is equal to 0 always. Why? What the condition?
Sir, because in case of our final expression, this can also be seen mathematically.
Yes.
Joule Thomson coefficient is given by this term, which is equal to Cp curly h by curly p at constant. This is our isothermal Joule Thomson coefficient, which is mathematically equivalent to. Now, in case of our ideal gases, since the force of attraction and repulsion are 0, so this term will be 0. So that's why our mu, Joule Thomson coefficient at isoenthalpic condition is 0.
Yes. And real gas is.
Since in ideal gas.
Yes. Sir. And for real gas is mu Jt is equal to plus positive value. Why? Other one is
for real gas is.
What will be the condition of real gas value for mu Jt is positive and negative?
Okay, sir. The value of real gas is according to real gases, mu Jt can be positive or negative.
Yes.
When mu is negative, since we have change in pressure which is always negative because we are dealing with expansion, then change in our temperature must be positive. That is T2 minus T1 greater than 0 when our system is heated. When temperature T2 greater than T1, only then our mu J will be positive. And in another case, when our system undergoes cooling, that is T1 greater than T2, in case of cooling, mu J will be negative. Mu J will be positive, sorry, because the negative term in denominator will cancel it out. So in case of cooling, mu J will be positive, and in case of heating, it will be negative. Is it true, sir? या फिर मैंने उल्टा कर दिया?
Real gas is condition is very high pressure, then will be no effect in mu J. So mu J value is minus.
Yes, sir.
mu J जो वैल्यू है रियल गैस के लिए, जब उसका प्रेशर हम
हाँ
हाई
जी सर.
करते हैं तब हमें नेगेटिव वैल्यू ऑब्जर्व होती है, यस प्राप्त होती है.
At high pressure.
यस.
At high pressure, mu J negative means there will be heating, sir.
यस.